Well, hello and welcome back. So we're moving on to topics 4.4 and 4.5 from the College Board CED. We're going to look specifically at Earth's atmosphere and global wind patterns and do our best to unravel the abstract idea that is the Coriolis effect. Please do your part and open up that textbook, the Miller textbook. The layers of the atmosphere is covered in section 19.1, pages 601 through 602. And much of the other stuff we'll be talking about with global wind patterns, etc., is in section 5.2, pages 124 through 128. All right, so let's talk about the atmosphere. I know we brought up a little bit about the composition of the atmosphere back when we did our biogeochemical cycles, but it is important to understand that by far the most abundant element in the atmosphere is in fact nitrogen. Nitrogen gas makes up nearly 80%, uh, with a distant second of oxygen. Now, those two by themselves are about 99% of the atmosphere. The remaining 1% is just sort of a mixture of lots of other gases. Some of our noble gases, like helium, neon, argon, krypton, etc., they don't really do much. They're inert. But also things like carbon dioxide, water vapor, etc. So that 1% remaining is a mixture of all those other gases you might have heard about that exist in the atmosphere. All right. Now, the atmosphere does lots of important things for us. So, first of all, it provides those essential gases for plant growth. So, we have carbon dioxide, of course, that plants need, oxygen for all other consumers. Nitrogen gas supplies nitrogen to the soil when it goes through the fixation process, etc. Now, aside from providing those essential gases, um, it is kind of worth pointing out that the atmosphere does have layers, so we'll get to here in just a little bit. Uh, but the density of molecules, so the number of molecules per like cubic meter, for example, is much, much higher near the surface, right? And so when you get to those outer layers of the atmosphere, even just a few thousand feet up, there's a big difference in the density of molecules. That's why when people try to climb and high up in the Himalayas when they get over 8,000 meters, for example. The air is so incredibly thin that they often need extra oxygen in order to supply enough oxygen to power their muscles. All right. But higher up in the atmosphere, in the stratosphere and thermosphere, for example, much of the really damaging radiation from the sun is actually absorbed before it reaches the surface. If we didn't have this thick blanket of gases above us, uh, there would be some highly dangerous and nasty radiation directly from our sun that gets to us, and it'd be much more difficult for life near the surface. Um, the gases in the atmosphere also help to moderate climate. Without gases that absorb and re-radiate infrared energy from the sun, we would get drastically cooler at night. So the temperatures would plummet very, very fast. Again, much more difficult for life without the mm, climate moderation. All right. Now, let's talk about the actual layers of the atmosphere themselves. The College Board does want you to know what these layers are and understand the temperature profile and understand a little bit about each layer. So we'll start down here in the troposphere. Now, this is where we live. All living organisms uh, are in the troposphere. So it is the only layer with biomass. So it extends up to about 10 kilometers. Now, even though it looks like the thinnest layer, which it is, this is most of our molecules are actually in the troposphere. Because again, the density of the atmosphere decreases pretty rapidly as you increase in altitude. So even though it's a relatively thin layer, it's packed full with the majority of the Earth's atmospheric molecules or gas molecules. Um, it's also the layer in which weather occurs. So when you see those giant towering cumulonimbus clouds, or what they call thunderheads sometimes, uh, they're reaching pretty high up in the atmosphere. They are staying well within the troposphere. All right. And temperature profile, and that's this red line you guys are seeing on this graph. As we increase altitude in the troposphere, the temperature decreases, which helps explain why it's so much colder at higher altitudes. Okay. Um, Now the stratosphere, which is the next layer up. Now we are getting to the point where airplanes. I don't know how good I am at drawing airplanes, but yeah, fly sometimes in that lower stratosphere, so they can fly up above those nasty storms, for example. All right. Um, the stratosphere, notice our temperature profile actually begins to increase again with altitude, and that's for a variety of reasons that we don't really need to get into right now. The other important thing to understand about the stratosphere and recognize is that's where our protective ozone layer is. So I mentioned before in the importance of the atmosphere being that it shields us from harmful radiation from the sun. Ultraviolet radiation, which is referring to a certain wavelength of light that would be really damaging to our cells. Much of that radiation, not all, but much of it is absorbed by the ozone, which is O3, by the way, in the stratosphere. Right? So that's the layer that contains that ozone. Two things to know about that. Temperature increases with altitude in the stratosphere. Ozone layer that protects us from ultraviolet radiation, also in the stratosphere. Now, the mesosphere, not a whole lot going on there, but temperature decreases with altitude. And then we get up to the thermosphere, way up there. Now, there's very little actual matter in the thermosphere. So we're getting up to the layer of the atmosphere where we could almost call it outer space, right? So little there. But a really important thing that does happen in the thermosphere, aside from the temperature increasing with altitude again, is that a lot of other radiation, like X-rays and other shortwave radiation, is absorbed there, right? So some of that shielding effect from those harmful rays of the sun occurs in the thermosphere. And it's also, if you guys have ever seen the aurora borealis, for example, the northern lights, that is the layer of atmosphere in which that is occurring. That is light being given off usually as a result of like solar like charged particles from the sun kind of running through the thermosphere there. Okay. And then basically what happens is not there's not like a really a defining line where atmosphere begins and outer space begins. It's just that the atmosphere essentially just keeps thinning until you get to a point where there's so few molecules left that you would just call it you've exited the Earth's atmosphere. All right. So those are the layers of the atmosphere. Now we're going to talk about wind patterns, global wind patterns specifically. Okay, so we have to understand a few basic processes before we get into the nitty gritty of like the Coriolis effect and the trade winds and the westerlies and polar easterlies and so on. All right, so we have to understand the role of rising versus sinking air. All right, what are called convection currents, and these occur on both small and large scales. All right. But essentially, what we have is we have solar energy passes through the atmosphere, heats up the air, and it heats up the ground. Now, air near the ground is going to heat up first and then radiate that energy out to the rest of the atmosphere. Now, because the air near the ground gets heated up more so, right, that decreases the density of that air. And it does say warm air rises, although it should be that warm air is pushed upward or becomes buoyant, would maybe be a better way to say that. But where we have rising air or air that is becoming buoyant because it's been heated, that creates a low pressure area. So basically, you can imagine that the atmosphere is pushing down on us, right? It actually has mass and weight to it, right? It's pushing down on us. When the air becomes less dense and is forced upward, that creates less of that pushing down or lower pressure. All right. Now, so now as that air rises into the atmosphere, it cools off, becomes more dense, and then sinks again. All right. So where we have sinking air creates an area of higher pressure. So lower pressure seeds clouds formation, right? So in locations where we tend to have air being forced upward, either through convection or sometimes by mountain ranges, right? That tends to correlate well with higher amounts of rainfall or precipitation. right? Areas where we have ongoing sinking air, right? So on the other side of mountains, for example, um, or at certain latitudes, right? That tends to correlate well with high pressure and less precipitation. So we'll notice at some point here, we'll talk about the kind of the global distribution of deserts. A lot of them are at locations on Earth where there's sinking air, ongoing processes like that. All right, so low pressure caused by rising air correlates well with increased precipitation. High pressure correlates caused by sinking air and correlates well with decreased precipitation and formation of deserts. All right. Um, Now we're going to talk about what are called Hadley cells. So now these are generalizations. These are not referring to what the primary causes of our daily weather. These are more climate influences, things that impact ongoing or long-term patterns in climate and weather. All right. So, so near the equator where we're getting our most direct sunlight, and we'll talk about the intensity of sunlight in another unit later on, or another part of this unit later on when we talk more about like climate and seasonal changes. But at the equator where we're getting our most direct sunlight, right? That tends to cause an area of low pressure, right? Because that more intense sunlight better heats the land surface, which heats the air above it, and that causes that rising air. Okay. Now, notice along the equator is where we tend to have those tropical rainforests, right? That's because we have sort of an ongoing process of rising air at the equator, which, as I mentioned before, correlates well with increased precipitation. Okay, now that air enters the upper atmosphere, cools off, and sinks. Okay, that tends to happen areas where we have the sinking air that tends to create areas of high pressure. So we have lows at the equator and areas of higher pressure at about 30 degrees north and 30 degrees south. So that's that first, what we call set of Hadley cells. Now, again, keep in mind low pressure, rising air, increased precipitation. High pressure is signified by sinking air and decreased precipitation. All right. So much of our desert formation around the globe occurs not exclusively, but much of it occurs at 30 degrees north and south. So the great deserts of, Sahara Desert in Africa, the Mojave Desert in North America, and so on. The Atacama Desert in South America, really dry places are relatively close to where we have those sinking cells of air, which reduces precipitation. Okay, a similar, although less organized pattern can be found at 60 degrees north and south. Oh, that's south, excuse me, 60 degrees north. So again, we get low pressure zones there, and then sinking air at the poles, which is why Antarctica and extreme northern regions are actually, while very cold, are also tend to be excessively dry. Antarctica is actually gets very little precipitation because of its location there, where we get the sinking air at the poles. All right. Now, another important thing to understand is wind is caused by differences in pressure. And in general, wind blows from high areas of high pressure to low pressure. My pen is acting up on me and it's getting annoying. Um, Air flows from areas of high pressure toward areas of low pressure. Okay, and that's what causes wind. So, um, when we look at general or global wind patterns, now we're not talking about the type of wind that just blows some days and not other days. We're talking about general patterns in the direction that wind flows, right? It follows pretty well these ongoing regions of high and low pressure globally, right? And so air is always going to flow from the high toward that low pressure region, okay? Um, Now, what is now causing, why are these, instead of arrows pointing directly at those lows, what is causing those arrows to actually be tilted away from that low a little bit, right? And that's what takes us to what we call the Coriolis effect. And again, this is a fairly abstract idea. I'll do my best to explain it, but we'll bring it up in class as well. So the Coriolis effect is due to differences in what they call rotational velocity, or the speed uh, of a given point on a rotational axis. So if we take the Earth's axis, for example, right here in the center, right? Now, we all know that the Earth completes one rotation every 24 hours, right? So one rotation requires 24 hours. Now, someone near or that axis of rotation, farther north or farther south, right, is going to complete a smaller um, rotation, or travel less distance in that rotation than somebody at the equator. So this would actually be, if I were standing, let's say at like 80 degrees north, right? And on that circle, I would complete one rotation for 24 hours. But the distance traveled in that rotation is less than somebody at the equator who also completes a rotation 24 hours, right? And because I'm traveling less distance in the same amount of time, I'm actually moving more slowly. So we could picture this as if we're moving counterclockwise, for example, in this case. Actually, we'll be moving, but anyways, let's just say, for example, that's the direction we're moving, right? A person here versus a person standing here at any given moment on that rotation, this person is going to be moving faster. And so if I could, right, picture this as like a merry-go-round, for example, right? As at the center of that merry-go-round, um, if I were to try to throw a ball at this person, because this person's actually moving away faster than the ball would be originating with me, that person would actually end up over here by the time the ball reached them. And to them, that ball would have the appearance of doing that. It would look like, so if I was here and this person were here and I threw it directly at them, because this person is moving that way more quickly than I am, if I were trying to throw the ball to that person, right, it would appear as though the ball curved away, when in fact the ball went straight and this person moved. Okay, so differences in rotational velocity is what causes that appearance or that relative motion to look like it swerves away from that straight line. When in fact, the ball did go straight from there to there, as you can see in this picture, but this person moved while the ball was traveling, making it appear that the ball curved like that. Okay, now that's essentially what happens with our global wind patterns, right? So we have low pressure and high pressure areas. Okay, now air is going to travel from high to low. Now, because at the equator, rotational velocity is higher, and in this case, the Earth would be spinning this direction. Okay, um, right? So if air moved from our high to our low, this at the equator is moving more quickly. It causes a sort of veering away. All right. Now, in that case, right, that causes the wind to seem as though it's coming from the east as opposed from directly north and south. And so this pattern of trade winds blowing more easterly from the east toward the west, right, is what causes that. Now, if we go to 60 degrees north and south, we also have low pressure regions there. So again, and then high at the poles and high at 30 degrees north and south. So the air is going to flow from high to low. Now, in this case, the air moving at from 30 degrees to 60 degrees north, this air is moving faster. So if I were um, standing here, right, it would seem as though the wind were coming out of the west. So much of the weather in the Pacific Northwest uh, actually comes from the southwest. And so if we could think about, so the U.S., Washington State's right about 45 degrees north. So we're right about here. So much of our weather comes out of that southwest because of that prevailing wind direction. Now, we will interact with the Coriolis effect in class some more so we can talk a little bit more about how to predict wind direction based on Coriolis effect. I just wanted to give you a basic intro, all right? And I want you guys to understand how high and low pressure, rising and sinking air, combined with the rotation of the Earth on its axis and rotational velocities cause these predictable and ongoing global wind patterns.